In this video, we will discuss the problem modified numbers and queries. The problem says that find the sum of all the numbers between the range L to R. So basically, we have to find a particular sum for all the numbers between the range L to R. Now let's quickly read the problem statement further. Here, each number is represented by the sum of its prime factors. For example, 6 is represented by 5 because 6 has two prime factors, that is 2 and 3. So the sum will be 2 plus 3, that is 5. Okay, so now if we will see 6, so for 6 the sum will be nothing but the sum of its prime factors. So 6 has two prime factors, that is 2, and another prime factor of 6 is 3. So that is why the overall answer for 6 would be 5. The sum for the value 6 will be 5 here. After this, if we see at the other example, so let's say we have 1, like let's say we have this range L is equal to 1, R is equal to 2. So in this particular range, if we'll observe, so L is equal to 1 and here R is equal to 2. Now, what we need to do here is, for 1, we can say that it will be 1 only. The sum of 1 will be 1 only. For 2, we can simply say that the sum of 2 will be nothing but 2. So in this range L to R, the elements that are present are 1 and 2 only. So the sum of 1 is 1 itself and the sum of 2 is 2 itself. So that is why the answer here will be 3. Now let's discuss the second test case, that is very important. So now if we will look at the second test case, which is quite descriptive. So now let's look at the second test case. So in the second test case, we'll be given the L value as 1 and will be given the R value as 6. Now if we will discuss this further, so we can say that for 1 the sum will be 1. For 2, the sum will be nothing but 2. For 3, the sum will be nothing but 3. For 4, the sum will be the sum of the, sum will be nothing but the prime factor, because you can see that for example, 6 is represented by 5 because for 6, 2 and 3 are its prime factor. So that is the sum. So basically here for 4, its prime factor will be nothing but 2. So 4 will be represented with the sum as 2. Now after this, if we look further, so 5 will be represented as 5 only, right? Because 5 for 5 only the prime factor is 5 only. After this, for 6 we can say that we'll have the prime factors as 2 and 3. So we can represent it as 2 plus 3, that is equal to 5. Right now, what we will do is, for all the elements in the range 1 to 6, we'll add their sums. So we'll add this 1 plus 2 plus 3 plus 2 plus 5 plus 5. Now after adding these values, the overall sum will be 18. So we have to return this particular sum. Now if you will see, so one thing that is very evident here is that we have L and we have R, and we have to find the sum in this particular range. So basically, if we think of doing this thing optimally, so one thing that can come to our mind is nothing but the prefix sum approach. Like we should have some prefix sum calculated. Like if we have a particular range L to R, so if we will loop in that particular range L to R and try to find our sum, so that will take a lot of time. For every query, it will take order of n time, right? But if we use the prefix sum technique here by some storing, let's say we store the answers somewhere, then if we have calculated the prefix already, then we can say that the answer will be nothing but prefix of R minus prefix of L minus 1. That is the thing. Basically, this is nothing but prefix sum technique, where if I have to find the sum between the range L to R, so I can basically say that the sum will be nothing but prefix of R minus prefix of L minus 1. I'm assuming that you know about the prefix sum here, because this is a prerequisite for this particular question. Now, what will we store in this prefix? That is another thing. So if we will observe, so basically for every number, we want to deal with its factors. And to be precise, we want to deal with the prime factors. So now for 6, we want to store for the value 6 in the prefix of 6, we basically want to store 2 plus 3, that is nothing but 5, right? So how can we approach this particular problem further? So now we can basically understand that since we have to deal with the factors, so if suppose that there are n numbers and we try to go to every number, right? Like let's say there's a value given, L is given as 1, R is given as n. So in that case, for one number, if we'll iterate and find the factors, so that will take under root of n time normally, because we'll iterate till the under root. Like for 36, we'll iterate till 6. From 1 till 6 we'll iterate, and then we'll get all the factors correspondingly, because 1 will give us 36 as well. So we'll iterate until the root n. So for one number, if we'll iterate through root n, so for n numbers if we'll iterate, so it will be n root n. So that is very costly. So do we have any better technique for iterating through the digit, like for iterating through the divisors of a number, or basically for iterating through the prime factors? Yes, basically we know that we have the sieve technique, which will help us to do this particular job in n log of log n time, right? So by modifying the sieve algorithm only, in case of the sieve algorithm, we decide whether a number is prime or not. So basically in this, we will modify the sieve algorithm that has been given to us, and then we will try to calculate our final answer. Because what we will be initially doing is, let's say we have been given the numbers. Let us say that we have been given the numbers. So let's say we have been given, let's say L is equal to 1, and let's say we have been given R is equal to suppose 10. So initially what we will do is we'll iterate through the array and we'll mark our prefix. So basically what we will do is we'll calculate our prefix in such a way that first of all we'll calculate the prefix, we'll pre-compute it for each and every value, and then in the end we will try to answer the query in order of one time by doing prefix of R minus prefix of L minus 1. So if we will try to do this, so first of all we need to calculate the prefix. So for that we need to write a pre-computation function that will run through the sieve algorithm, and in n log of log n time it will calculate the prefix sum. So what we will do is we will basically first of all say that we need to have a prefix array. So we can simply say that we will declare a prefix array, and here what we will do is initially if we'll see what should be the size. So we can basically see that the size can be 10 to the power 4. So what we will do here is we'll iterate and we can simply mark it as 1 0 0 0 1. That is 10 to the power 4. So first of all we'll declare its size as 10 to the power 4, right? After this part what we will do is we'll write a pre-computation function that will help us to pre-compute the results. So what we'll do is we'll write we'll write a pre-compute function, and in this pre-compute function we'll try to run the sieve algorithm that will help us to store the sum. I'll be talking about it in the later part, just after writing the main function. So what we will do here is we'll write the pre-compute here as well, and this pre-compute function will, after that it will run and it will fill the prefix array for each and every element. So after this, let's say we have pre-calculated the result. In that case, what we will do in the end is we can simply return the prefix of R minus prefix of L. That is what we usually do. Let's suppose that prefix sum array is already calculating the sum. So we'll do what? We'll return nothing but prefix of R minus prefix of L minus 1. In this part, what should we do? So we can simply say that initially we will initialize every prefix index as 0, because initially we'll initialize the sum of every element as 0. So what we will do is let's say we have been we have 1 to 10. Suppose that we are developing the prefix array for 1 to 10. So basically what we'll be doing there is we'll simply start and we'll simply say that let's first of all mark all the indexes as 0. So what we will do is we'll simply have this particular array that is for, let's say, size 10 initially. Obviously the answer will have 10 to the power 4 size, but we are drawing it till 10 only. So we'll have 0 index 1 2 3 4 5 6 7 8 9 and 10. After this has been declared, so we will do what? First of all we'll mark every index as 0. So basically we'll fill every index here as 0. So let's quickly do it. So what we'll do here is we'll say that I starts from 0, I is lesser than the 1 0 0 1, then I'll do an I plus plus, and after this part is done, so what we'll basically do is we'll mark the prefix of I as 0. So initially we'll mark every index as 0 because initially it does not have anything. After this part has been done, then we will proceed further. So in this part, what we'll be doing further is we will simply say that you can observe that for one, like initially suppose that every element has been filled with 0. After this part, what we will do here is we will fit for 1. If you will remember, for 1 the answer was 1, for 1 the sum was 1. So now we will update the prefix of 1 as 1. So we'll say that prefix of 1 is equal to 1. Basically we'll update the sum. Basically currently we have not taken the prefix, like we'll in the end whatever will be stored, so after that we can take the prefix, but first of all we are basically storing the sum for 1. Okay, after this we can simply say that we'll start iterating. So how does the algorithm work? So we know that in the sieve algorithm, what we do is we say that for I starts from let's say 2 and I is less than 10 to the power 4, less than equal to 10 to the power 4, then we'll do an I plus plus and we'll check like what we can do. Like if let's say what we do here is if the prefix of, suppose after this we have marked this as 1, and if the prefix of I, right, if the prefix of I, if the ith prefix is equal to 0, then what does that mean? That means that it is a prime number, because if let's say 2 is here, 2 is currently 0. So this basically indicates that if currently I is standing at 2, so prefix of I, this particular value will be 0. So what does that mean? That means that 2, the ith number, is a prime number. So if it is a prime number, in that case what we basically need to do is, we need to say that for 4 we'll update the sum as 2, right? For 6 also we'll update the sum as 2. For 8 also we'll update the sum as 2. For 10 also we'll update the sum as 2. So for all the multiples of 2 that is starting from 4, we will update their sum, will add 2 to their sum, right? We'll update their sum as 2, because 2, like if the ith number itself is 0, in that case what we can simply say is that we can iterate further and we can mark them with the, because 2 is a prime factor. So in that case what will happen? For 4 we can say that 4's sum will increase by 2, because 4 will have a prime factor 2, 6 will also have the prime factor 2, so its sum should increase by 2. After that 8 should have a prime factor as 2, so it will have the sum increase by 2. 10 will also have the sum increase by 2. So now this will happen. So basically what we'll do is, we'll say that I will iterate. Now notice that I have not incremented the sum of 2 yet, so I'll do this later on. So what I'll do here is, I'll say that okay, let's start our j from 2 into I, that is from 4. Like basically if I is starting from 2, then j will start here from 4. If I is starting from 3, then j will start from 6. Then what we will do here is, we'll say that j is less than equal to 10 to the power 4, j plus plus, like j plus is equal to I, because first of all we'll be incrementing 4, then we'll be incrementing 6, and then 8. So the multiples of 2. So we'll iterate through this, and we'll say that the prefix, this part, the sum for the jth index, for the jth multiple, that is for 4, 6, 8, 10, all these values, their sum should be increased with I, because I is a prime factor of them. Because you can see, if I was equal to 2, then 2 is a prime factor of 4, 6, 8 and 10. So what I will do here is, I will simply say that now, after this part, I'll simply say that we will iterate for int I starts from 2, and then I is lesser than equal to 10000, that is 10 to the power 4, and then I plus plus. So we'll increase for every I, and then what we will do is, we will say that if it happens that, like we will, if it happens that the prefix, if the prefix of the ith number, if it's equal to 0, so that means that ith number is a prime number. This basically will indicate that ith number is a prime number. So if ith number is a prime number, in that case this prime number should be added to all of its multiples, because if 2 is a fact, like if 2 is a prime number, then 4 in the 4, this sum should be added. For 6 also the sum should be updated with 2. For all the multiples it should be updated. So what I'll do here is, I'll simply say that for int j starts from 2 into I, and then j is less equal to 10 to the power 4, so 1000. Then we'll do a j plus is equal to I. So it will keep on updating the multiples. So we'll say that j plus is equal to I. After this part is done, so what we will basically say that is that prefix of the jth element will get updated with the sum as I, right? Let's see. So after this, let's say I was equal to 2, so it will update all of its multiples with the sum as 2. And after this part is done, so let's say after that I moves to, let's say after this I moves to 3. So when I will move to 3, then we will observe that if I will move to 3, then after that we can see that prefix of 3 is also marked as 0. So in that case, all the multiples of 3, like 6, 9 and all the other elements, should get their sum updated with 3 as well, because 6 is having 2 already stored in this sum. You can see here 6 is having 2 stored. Now it should get it should store 3 as well. It should store 3 as well, because 3 is also a prime factor of 6, because 3 is itself a prime number. So that means 3 is a prime factor of 6. So in the prefix of 6, I should update 3 as well. So that is what I'll be doing again. That if it happens that suppose I is standing at 3, if I is equal to 3, then in that case we will start our j from 6. Like basically our j will start from 6, and j will keep on moving like 9, 12. All the multiples will be indicated by j, and for all those multiples, they will get updated with the sum. Their sum will get updated with I. What is I is 3 here. So all, because for 9 also I should update its sum as 3, and for 6 also it's whatever sum it was earlier storing, plus the current prime number, that is 3, because 3 is also a prime factor of it. So now what will happen? 6 for 6, its total sum will become 5, because 2 plus previous sum was earlier 2 stored, plus 3, that will become 5. After that, if I'll see for 9, so for 9 also I'll update. So 9 had earlier the sum as 0. Now it will get updated to 3. Right after this part, what will happen here is, once this much part has been done, so we will do it for each and every index. So now you will see that for 4, when I'll come to 4, so will I do it for 4 when I is equal to 4? So when I will be equal to 4, then I will not be doing this particular process, because I can see that prefix of 4 is not equal to 0. Why? Because it is not a prime number. So if it is not a prime number, that then it will not be added in any of the numbers of its multiples, because uh, for every number its sum will be nothing but the sum of its prime factors. 4 is not a prime factor of any number. So that is why 4 will not get added to anybody. After that, we'll move to 5. So when we move to 5, so we can simply observe that 5 is having the sum as 0, because prefix of 5, if we'll see this array, so prefix of 5 is nothing but 0. So that means 5 is also a prime factor. So if 5 is a prime factor, so all the multiples of 5 should get updated with the sum as 5. So in this case, if you will see, so 10 is having already the sum as 2. Now for 10, 5 is also a prime factor. So we'll iterate through the multiples. With this j loop, j will start from 2 into I, that is j will start from 10, and j will move on 15, 20 like this. It will keep on moving like this, and it will update for all those numbers. Whatever previous sum they are storing, it will update their sum with 5 as well. So what will happen? 5 will also get added. So for 10, the sum will now become 7, because 10 has two prime factors, 5 and 2. So 5 plus 2 will be nothing but 7. That is what is indicated here. You can see here, I will be iterating. If like I will be equal to 5, then I'll be iterating from 10 until the end, and then I'll say that for the jth multiple of I, I'll update its sum with I, because that needs to be stored, right? So this is one thing that I'll be doing for all the indexes. After that, let's say I'll move to 6. So when I'll move to 6, then 6 is not having the sum as 0, because it is not a prime factor. So after that, we'll move to 7. Now 7 is having what? 7 is having the sum as 0. So its multiples will get added with 7, but currently I have not written it. But obviously 14 will have the sum 2 stored already. Then 7 will also get added, because 7 is also a prime factor of 14, right? After this, what will happen is, we'll move to 8. Now 8 is not a prime number. 9, because it is its prefix is like its value in this array is not equal to 0, right? Because it has some factors, right? After this, 9 is also not prime. Then 10 is also not prime, right? So we have written it till 10 only, so that the explanation is a bit short. You can try it for longer array as well. After this part has been done, so do we need to we will take the prefix sum, right? That is one thing. But before doing this, if we'll observe this particular array, so there is one thing more that is missing. We can see that we also need to update the prime numbers. We can see that 2 is not updated, so 2 sum should be updated to 2 first of all, right? So first of all, let's update the sum of 2 as 2. So after coming out of this loop, we can simply say that prefix of 2 is equal to 2, because for 2 the sum will be nothing but 2. So we'll update the prefix of 2 as 2, right? After this, what we can observe is all the odd prime factors, right? All the odd prime factors, which are equal to 0, which are still equal to 0, they need to get updated, because you can see 3 is an odd prime factor, it is 0, so it needs to get updated with 3 actually. Similarly, 5 is also an odd prime factor, which is 0, so it needs to get updated with 5, right? Because 5 can be represented with sum as 5, because 5 is a prime factor, right? And after this, if I'll see further, so 7 is also a prime factor, which is odd, and it is having value 0, sum current as 0, so it should get updated with 7, that is itself, right? And so on and so forth. But 9 will not get updated, because 9 is an odd number, but it is not a prime factor, right? So that is what I should be doing with the help of a loop. So what I'll do here is, I'll run a loop. I'll now simply run a loop. Now int I starts from what? I will start from 3, and I will be lesser than equal to 10 to the power 4, 1 0 0 0, and then I'll do an I plus plus. Now once I do that, so in that case, what will happen is, basically I'll say that if it happens that the current number that I'm at, if it is having 0 in its at the value, if it is having 0, so that this basically means that it is a odd prime factor. So if it is a odd prime number, in that case, what I'll do is, I'll simply say that prefix of I needs to get updated with uh, I itself, right? Because for 5 the sum will be 5, for 3 the sum will be 6. That is something that I need to update after coming out of this loop, right? Now what has happened now? So if you will see here, so now let us try and cut the size of this array. So let's say that we have this much array only. That is the first question that was asked. So suppose we have one, we have this particular array for index. So let's say the index is 1 2 3. We are cutting the array from here till here. We are taking it till 6 only. So we'll have 1, 2, 3, 4, let's say 5, 6. Okay, so we'll have the indexes like this. After we have the indexes, now what we will be doing here is we need to like the sum is stored basically in the prefix array. Currently we have not taken anything like prefix. Now we have just got the sum like 1, 2, 3, 2, 5 and 5. Now if somebody will ask that okay, I'll give you the range L as 1 and R as 6, now tell me the sum. So will you iterate from this range till this range in the prefix, and you will calculate the sum as sum plus is equal to for every I from for I starting from L, I is less equal to R, I plus plus. Will you do this thing that I plus is equal to prefix of I? No, if you will do this, that will take order of n time in the worst case. So for every query, if there is one query, you will take order of n time. If there are q queries, you will take q into n time, which is very high. So we will try to answer the query in order of one time. That is why we have named this particular array as prefix array. Because currently you could have said that this particular array is nothing is prefix here. It is nothing but sum array. But I declared it as prefix array because now we need to take the prefix sum. Because if we want to answer this, so what we can say here is that after this what we can basically say is that if we'll observe, so we'll try to take the prefix sum. So what we will do here is we'll take the prefix sum. So we'll update this particular prefix array with the previous sums. So what we'll do here is in this case we'll start iterating. So we'll say that okay, for I starts from let's say the starting. So the starting point is let's say 1 here. Then I'll do an I is lesser than equal to let's say 10 to the power 4 here. But basically here I have the size as 6 only. So let's say I'm doing it till less than 6 equal to 6 I plus plus, right? And then what I'll say is I'll say that okay, prefix of I plus is equal to prefix of I plus is equal to prefix of I, like the ith prefix sum will be will be equal to the previous as well, right? It will get the previous sums updated in it. Why? Because after this what will happen if I'll update this? So now this particular sum will become 3 because 2 plus 1 is 3. Then after that this is 3 and the previous sum is 3. So this will become 6 here, right? This will become 6. And now the previous sum for this, when I'm at this 4, then the previous sum is 6. So I'll update this thing with 8. And then what I'll do is if I'll move further, so after this we'll have we are at 5. So when we are at 5, in that case what we need to do, when we are at 5, then the previous sum is 8. So we'll update this thing. So now it will become what 8 plus 5 will be nothing but 13. And after this we'll move to 6. So when we move to 6, so we'll add the previous sum that we have calculated up till now. So previous is 13. So that is why what will happen, basically this will get updated to nothing but 18, right? After this, if you will observe, if somebody will ask us that okay, what is the sum? So in that case what can we say? Like if somebody will ask that okay, what is the sum? So we can simply say that it is nothing but according to the prefix technique, if we are asked that okay, tell us the sum between L is equal to 1 and R is equal to 6. So that will be nothing but prefix of R, you can say, right? Prefix of R minus prefix of L minus 1 as per the prefix technique. So that will be what? Here we can say that it will be prefix of 6. So prefix of 6 is nothing but 18. And prefix of L minus 1 will be nothing but 0. So we'll subtract 0 from it. And that is how efficiently in order of one time we'll get the sum as 18. Right. So that is why we have written this thing. So let's quickly write this here as well. So what we'll do here is after this we'll iterate. So we'll say that okay, int I starts from let's say we can mark it as 2 initially, right? And then I is less than equal to 10 to the power 4. Then we'll do an I plus plus. And after this part has been done, so we'll simply say that prefix of I plus is equal to prefix of I minus 1. Right. So that is how we'll update the prefix sum. And we can see that in the function, we are simply returning prefix of R minus prefix of L minus 1. Okay. Now let's quickly try to submit this code first of all, and then we'll talk about the time complexity and the space complexity taken in this particular code. Okay, so we are getting some errors. Yeah, so I have declared these things. So that is why I was getting errors. Now let's try and see. It works on the samples. Let's try and submit this code as well to see if it is working or not. So you can clearly observe that in the very first go, our solution was able to pass all the test cases that are given it. Now talking about the time complexity of this code and the space complexity. So first let us address the time space complexity taken in this particular code. So what is the space complexity taken in this particular code? Space complexity taken in this particular code is nothing but order of n. Why? Because we took order of n space for developing the prefix array. So that is why the space complexity is nothing but order of n, because we had to take this particular prefix array, sum array, so that we can answer all the queries in order of one time, right? That is what we did. Now talking about the further time complexity part. So if you'll observe the time complexity of our code, So according to the time complexity, if you'll observe, so if you can see here that if we are given a range L to R, then we are answering the query in order of one time, because accessing the array elements is the constant time. Prefix of R minus prefix of L minus 1 will be done in order of one time. But the main complexity will be for the pre-computation that we are already doing. The prefix sum, the overall sum that we are calculating using the sieve algorithm as well. That is what is taking time here. So in this case, what we can observe is, see, first of all, we are running order of n times, you can say, for initializing everybody as 0, right? So let's update. So order of n time for initializing everybody as 0, right? Then after this part, what we are doing is, we are running this particular algorithm. So this is this algorithm that we are running from I starts from 2, I is less equal to 10 to the power 4, and then running for all the prime factors. Like the J loop is running for all the prime factors. I'll try to derive this particular complexity as well. So you can stay till the end to understand the time complexity of the sieve algorithm if you don't know it, right? So in that case, what will this be? This part, like this is running, the overall complexity of this algorithm is nothing but n log of log n. So I'll derive this by the end of this video as well. It will be order of n log of log n. Let's assume it for now. Like we can say it will be the complexity for C, but I'll try to show you why it is so, right? After this part, what will happen here is, you can see another order of n traversal we are doing, right? So another order of n traversal we did for all the prime numbers, for all the prime numbers that were odd. After this, we again did order of n traversal for this part. That is the calculation of prefix sum. Actually, the array that we are using, the prefix sum. So that will take another order of n. So if you will see, the overall complexity of this code will be nothing but order of n log of log n. That is the overall complexity that is taken by the sieve algorithm, sieve of prime. That will be the highest n. So this will be the time complexity, right? So basically the prerequisite for this question was that you should be knowing the sieve algorithm and the prefix sum technique. Okay, then the question becomes very easy. But still, how does the sieve algorithm have n log of log n time complexity, right? You will say that, okay, how does it have n log of log n time complexity? So I'll say one thing. When is my loop running? When does my loop run? Right. So if you have to understand one thing, so let's say if I have I is equal to 2, when I was 2, then the loop will be running, because the loop J loop will be running for what values? For I is equal to 2, I is equal to 3, I is equal to 5, I is equal to 7, right? Basically for all the prime factors it will be running, right? So for how much time it will be running for I is equal to 2? How much time J loop will be running? So we can simply say that the J loop for I is equal to 2, the J loop will be running for how many times? If suppose we have the value is n, right, the highest value is n, so it will be running for how many times? How many factors for it? Will be running. If I give you n is equal to 50, then I can simply say that it will run for 2, 4, 6, 8 up till 50, correct? So that is, it will run 25 times, okay, correct? Because there are 25 factors for it needs to run. So that is nothing but n by 2, right? So the J loop will run n by 2 time when I is equal to 2. Then after that, if I is equal to 3, then also it will run. So when I is equal to 3, then how many times it will run? Right. So suppose that I gave you something like, let's say n is equal to, let's say, 10, basic thing. So in that case, you will say that it will run 3 times, because it will run for what? 3, 6, and like basically you can say indirectly say that it will run for 3, 6, and 9, right? Basically the factors. Okay. So that will be how many factors are there till n for 3. So for 2, if we see for 2, n was equal to 50, then I was running for 2, 4, 6 like this till 50. So alternatively, so that was 25 times I was running, right? So that was nothing but n by 2. So for 3, it will be nothing but n by 3, because n by 3 factors are till n, right? You can try to check it out as well for a sample case, right? If I give you, let's say n is equal to 10, so the number of factors till 10 is nothing but 3, 6, and 9, right? The number of like the number of multiples, like for 3, I have 3, 6, and 9 here. So after this part is done, so we can say that what will be the complexity when it will run for 5. So when I is equal to 5, then the loop will run for n by 5 times, right? Because n by 5 factors will be there. Because I give you n is equal to 10, then 2 factors will be there, 5 and 10 only, right? Two multiples basically. After this part, how much, if I is equal to 7, how much times it will run? It will run n by 7, right? And you can continue this series forward. So now if you will take n common, right? If you will take n common, so you can take n common, and the series will look like n by 2 plus 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7, right? Now you can see that n is taken as common. Now this is nothing but a series. I think this is a harmonic series, you can say. So this has a special property. So basically the sum of this series, if you will solve it mathematically, you must have learned about it in class 11th. So if you will solve it mathematically, so the sum of this series will come out to be log of log n. Okay. and n is already common here, right? So it will be nothing but n into log of log n. So that is nothing but n log of log n. That is how the formula comes. If you have stayed till the end in this particular problem and you have understood everything about this problem, how we did it in n log of log n time using the sieve algorithm and the prefix sum approach, then make sure to hit the like button, comment down understood as well if you have understood till now everything and the derivation of the sieve algorithm. If you don't know about the sieve algorithm, you can first of all read about it and then come back to this problem as well. But I hope that I have explained the sieve algorithm because sieve is the prerequisite for it. So make sure to comment on understood if you have understood till the end, and don't go without subscribing the channel if you are coming for the first time. Thank you for watching this particular video and keep coding.